All right, so let me self-introduce myself. I'm David Pan from UT Austin. I'm a Silicon Labs endowed chair here, and also today I'm wearing my Silicon Catalyst hat as the advisor. All right, so. But my talk is, talking about the underlying all kinds of different technologies and trends for the future chip design, in particular AI for chip design and EDA, right? So, it doesn't work. Right? Okay, I'll just do this. So I think in this audience, I'm sure you know all the flow. Here, I'm just showing you the big over. Let me actually turn on the mouse, the laser pointer. Yeah. So as you can see, right, so this is a very top-down flow from system specification to, logic, physical design, and then design for manufacturing, and ultimately fabricate, packaging. And in the entire process, right, it's super complicated. And you may take iterations, right? So because of these iterations, the design cycle is really long and complicated. And then you may wonder what AI can do, right? So AI actually can serve as hammers. Of course, people may joke that just a big hammer try to find the nails, right? But hey, it is indeed, we want to find the best match between hammers and nails. And indeed, actually, if you go to the top conferences, by the way, I'm also wearing my DAC shirts. I'm the DAC executive committee and serve as a vice chair this next year in Long Beach, and the year 2027 I will be the general chair. And DAC is a flagship conference. But you can see the number of submissions grow like Moore's law in the last few years, and AI is big everywhere, and in terms of optimizing PPA, and of course in this conference verification, right? And everywhere, all levels of design abstraction in digital, analog, RF, and verification, right? So, but not yet all at once. I think this morning, some keynote speakers talk about, hey, we still need the designer expertise to really interact. Am I? Oh. All right, let me still turn on the, I think, laser pointer. Okay, all right, let's quickly go through. Yeah, so I think I already went through these slides. So, well, basically in the next, let me see, try to keep on in the next 15 minutes or less, right? And I'll quickly kind of give you a roller coaster ride for all different aspects of AI for chip design. And so including, as you can see, the front end side, like our AI for RTL and Verilog design. And later on, I'll jump through the physical design, and then I also talk about analog and RF or even photonics, 3D heterogeneous integration. Anyway, since this talk is not just a verification, so I think I can share with you from my kind of academic perspective and also as some startup advisor and different roles, right? What are the really emerging trends? So AI for software coding is already very widely successful, as we all know, right? Because and they're doing really good job. And also in terms of RTL generation, many papers have been published here. I just show you an incomplete set of all the recent, different kind of, Verilog generators. You can see the names. There are so many different acronyms, but the problem is that they are still not. They can still guarantee correctness. And not to mention, wow, you want, the real experts, they want PPAs, right? So what kind of RTL can give you good PPA? That's still a big, question to be asked. And hardware language compared with software is much harder because there's tremendous amount of concurrency and so on and so forth, right? So here I just showed two recent work. One is from Verilog Coder from NVIDIA Research, headed by my former PhD student, Dr. Mark Ren's group. And basically, they use some kind of abstract syntax tree. Essentially, what is the key idea here, right? Essentially, when you are trying to do RTL generation, you want to insert some kind of formal guidance or checking, right? So to ensure you have some kind of correctness. So either using this, or there's also another work from University of Central Florida using some control data flow to analyze the control logic, and then you can, hopefully do better. But all this work still sacrifices some, suffer some limitation in the sense that, usually you still generate Verilog, ultimately you still have to verify it, right? And we know that verification problem is such a hard problem. So actually my postdoc, Dr. Yoli is here. He's actually working on some new direction, which we are trying to do a stepwise verification during the design process. The key idea is like, hey, can we even do it correct by constructions? Instead of waiting until the very end, we are going to do more kind of early stage, right? Anyway, this is still ongoing research, right? Emerging trend. And in terms of the more core physical design, right? RTL generation is a big chunk, right? And then the next big chunk is RTL to GDS2, right? The company spent tremendous amount of time and, to beat all the PPAs, right? So my group, in collaboration with NVIDIA Research, we published Dream Place, which actually have got a dual best paper award from the top conference and journal, TCAD and TCAD. Basically, we pioneered deep learning inspired GPU acceleration for placement, because that is a very, very important, crucial step. And we even put the original version open source, and I just noticed yesterday, right, 888 GitHub stars. Interesting. I didn't even know that there are more than 800 people interested in developing placement, right? But anyway, it's widely used by industry now and also academia. So one of the big direction of this is that while you are doing this, ultimately, to really leverage machine learning, you want to reformulate some of the problem into a so-called differentiable formulation, so that you can leverage all this GPU acceleration, forward, backward propagation, and so on and so forth. Right? For example, this year's DAC best paper award also actually went to NVIDIA Research, actually again by Mark Ren's group in NVIDIA Research, and they actually proposed a differentiable SS static timing analysis, and then combined with timing-driven placement, they show the state-of-the-art result, right? And then moving forward, to the manufacturing, we know that Moore's law is kind of stopping in the sense that, well, they're still scaling, but the gain from intrinsic scaling is really not too much, right? So this is a keynote talk from Mark Peppermaster, by the way, he's a UT Long Haul, right? And so he gave a keynote at DAC 3 years ago. He basically says, hey, look, this is the intrinsic scaling. So in the early days, most scaling is from technology, right? But then as you move on to 7, 5, 3, more and more, the basic intrinsic scaling is getting less and less, and more is from so-called DTCO, design and technology co-optimization, such as the standard cell library optimization, how many rows, and all kinds of stuff, right? And so I think that's where really we can get more juice, right, out of the fruit, right? So then, so far I have talked mostly on the digital side. Let me also move on to the analog and RF side. The real world is analog when I'm speaking. I'm not just digital, right? So 5G, 6G, physical, robotics, sensing, and so the real world is analog. Even actually digital computer, you may think, wow, okay, my CPU, GPU, they are so cool, so powerful. Even those digital computing systems are analog enabled. This is actually a keynote that I heard from Professor Sujie King Liu. She was the dean of UC Berkeley until very recently. She is she is the National Academy of Engineering president now. Basically, she says that, hey, even digital analog enabled, in the sense that even for your digital computers, like your CPU or GPU, there's many kind of temperature sensors. Otherwise your chip will burn, right? And also, of course, I/O is so important. The bottleneck is not really how fast you can compute, but how fast you can really transmit, get the data in and out, right? So all those, as you can imagine, a lot of analog components. So if you don't have any of that, your modern computer will work like a 486. That's 20 plus years ago, all right? So there are, of course, a lot more stuff, right? Anyway, but analog and RF designs are really hard in the sense that, this is a famous graph from a classical textbook from Professor Razavi. And analog, not like digital, is very well, PPA, right? So it's very well defined. But analog has so many weird stuff, all kinds of objectives, and they tweak it, everything can't. And because it's analog, so it's very sensitive to all your, from design to sizing to the physical layout, right? So the conventional flow is like, hey, you just have to run all bunch of simulations, and the experience, the gray hair engineer was, oh, maybe we should tweak here and there, but it's tremendously time consuming, right? So along this line, actually, my group has always also been pushing this so-called end-to-end analog design automation paradigm, in the sense that from topology to sizing to layout, and we're trying to build this kind of closed loop kind of iterations, and machine learning definitely helps, right? And also agentic AI can serve as a design agent, a co-pilot. So led by a previous DARPA project, we at UT Austin, we proposed the magical layout systems. I won't go into details, but basically you have a netlist, spice netlist comes in, and through our magical layout systems, we will have layout comes out. All right. So of course it's kind of like a magical. Okay. Yeah. Okay, yeah. So we open source the first version, and it already also get several hundred, GitHub stars. And but I think there's definitely a lot of opportunities to continue improving. I have quite a few students still actively working on this. We have chips tapped out, and previously, if you are a manual designer, it takes months, right? We're using our tool, push a button, and minutes, right? You get layout. We also have SAR. It's a pretty advanced, analog chips, right? So as you can see. Then, so moving up, from a layout, sizing is a very, very important step. Although you may not have too many transistors, but each transistor is kind of continuous. You are tweaking this huge solution space, right? So, here I'm just showing you some, specs or what kind of requirements, and you still want to minimize power and this, but the solution space is kind of continuous, right? So what actually we have proposed along this line, we are the first to use reinforcement learning to do this, and we got a state-of-the-art result, meet very stringent design specs, and so on, right? So, and then we are saying, hey, now let's even move up to the a topology generation, right? So of course, a typical conventional flow is like, oh, we will generate topology, then do sizing, then do layout. But okay, this you may have to go back and forth, right? But anyway, so we proposed a method to do sized topology selection. Again, I won't go into details. And this project also sponsored by SRC. We got the first place last year, right, in their annual review. Now, along even further on up, right? So actually, we will say, hey, how can AI and LLM, which is very hot now, right? And agentic AI can help, right? So actually, there's a lot of work in the, as I mentioned, LLM for RTL generation, right? But not too much for the analog circuit design. We are the first to propose this analog coder, essentially using LLM to really help you to even come up with non-trivial analog netlist, right? So we published a paper at this year's Triple AI, which is a flagship AI conference. In just I don't know, less than 8 months, we already have 80 citations. It's pretty impressive. It's a very, very active research area. So again, I won't go into details, but this one is training free, but we have smart prompt engineering, feedback mechanisms, and our methodology to deal with this. Again, I won't go into details, and also our newest version even can handle multimodal with basically waveform, not just text, but we can use waveform with some simulation and waveform to help you to do kind of generation, and also we will do sizing to do the optimization, right? And then talking about RF, right? RF is even a little bit niche in the sense that compared with analog, right? So, but RF is tremendously important. Think about all the modern satellite communications, your cell phone, there are all kinds of Wi-Fi's there, right? And the RF there, right? And but the RFIC again is even more like a hand optimized. RF has active as well as passive, and interestingly, passive for RF is a bottleneck. Essentially all kinds of matching network and so on and so forth is very complicated. Here's a conventional flow, right? Basically, you will have some, designer has some templates. They think, okay, let's try to do all the simulations, and then they get some results, and they do all these iterations, right? It takes a tremendous amount of time. what we proposed the pulse RF flow. Basically, give me a spec, I can directly give you the inverse design for your passive design. But of course, how can you do that, right? We have several enabling technology like physics augmented machine learning models for faster, forward evaluation than using inverse design. And we actually can get superhuman, non-intuitive designs. Actually, inspired by this project, and actually I led the UT Prime team to win the very first CHIPS Act. They have this national NSTC, National Semiconductor Technology Center, $7 billion, R&D center, the first project, right? But we run the project for 5 months, but unfortunately, because of the political thing, right? So NetCast is now been terminated. So we'll see how to revive this effort. But from a research perspective, we already have good prototypes. We also even have some small startup to try to even commercialize some of these efforts, right? So look forward to collaborate. And then, okay, so let me also talk about optical, right? So I'm sure that computing is important, but optical and all this, communication is very important. I won't go into details, but optical has always been next generation interconnects, but now it's really, look at all the newest GPUs and even TPU that have optical links. So we also have done optical computing. We have published a lot of papers on this, and I think this is also very, very interesting. And last but not least, hey, ultimately, you have digital, analog, RF, photonics, emergent memory. So 3D heterogeneous integration of all these will be the way to go, right? If you want to build the future big systems. But to do that, you need all kinds of AI-driven EDA tools for modeling, optimization, and system technology co-optimization. Actually, just for your information, UT Austin, we have this Texas Institute for Electronics. Last year was awarded, I think, largest DARPA project, $840 million, plus Texas State invested $560 million. Altogether, is more than $1.5 billion to set up a state-of-the-art advanced manufacturing fab at UT Austin, and also to build these ecosystems. So actually, interesting. Even more than 10 years ago, my group worked on those kind of reliability for TSV and. But anyway, when you are doing all this 3D heterogeneous, there are all kinds of effects you need to consider, right? All right, so just to conclude, for chip design is definitely everything everywhere, and there's tremendous opportunities. Verification, of course, is is the main thing of this conference, but there are a lot more, and all kinds of challenges I'm sure you have heard about, and not yet all at once. That's my dream, but I don't know whether it will happen. But anyway, so interestingly, I actually had an interview with I don't know, ACM is basically, you are aware, ACM is like IEEE is the biggest computing organization. They interviewed me back like more than 3 years ago. Half a year between ChatGPT was released, right? I was like, say, hey, my dream is to have a silicon compiler which can let people design chips as easily as they can to write software. That's still my dream. Okay, so hope this will happen one day. Okay, thank you.